Hi, in this video we'll be talking about the idea of divide and conquer. What is this divide and conquer that people speak of in solving problems? So divide and conquer is just a problem solving paradigm where you use these three key steps to solve any problem. You divide the initial problem into smaller parts. So you're given an initial problem that is something like this. You divide it into smaller parts. Okay, so these are smaller than the original size. Okay, and then conquer them. How? You can use a recursive technique that this can be solved same as this original one. So you can even divide it into smaller parts unless you get very small that you can solve it very easily or trivially. And then once you have the solution for very small parts, you merge them back into the array or solution state that it came from. Okay, and get the solution for that state as well. Okay, so you get the solution for this state, and then this returns its solution to this part, this returns its solution for this part. You need to combine the solutions from two of its child coming into this node and get the idea. So this is like a recursion tree that we are forming right over here, but simply saying this is like a solution problem that you need to find answer of, and this is the smaller solution states that you are going into. Like this is the problem that you need to solve, this is the problem you need to solve, and then combine the solution of these two solutions and get the solution for this original problem. Okay, so problem is given to you, break it down into two smaller problems, get the solutions of those smaller problems, combine those solutions to get the solution of the original problem. Okay, so this is the whole idea of divide and conquer. Divide, conquer the smaller parts, and combine the solutions to get the solution for the original problem. Okay, so one classic example of divide and conquer is merge sort, which is you're given an array, you need to sort that. So what we do in merge sort is that we first of all have the array and we divide it into two parts. We just hypothetically divide it into two separate arrays, smaller arrays of size equal size n by 2 and n by 2, and then recursively solve them, or we conquer them using the same technique that we used over here. Okay, for the larger array, if we can solve it, then we can solve it the smaller parts as well using recursion. And then suppose we now know the solutions of the smaller part, how can we combine the solution for the larger part? So this is how recursive ideas work, that if you can solve the smaller instances and get the solution, how will you merge the solution? Okay, and if you can do it at this level, you will be able to do that in the smaller levels as well. So over here, if you can find a way to merge the answer that you are getting from these two arrays, you can use that same technique over here as well, right, to get its solution merged from two of its smaller subarrays, right? So that's what being used over here. And for merge sort, this works like a charm, that you can divide the array into two parts, sort it individually, and then merge it. So what is the time complexity of the merged part? So there is this t of n recurrence, that t of n is how much time it takes to sort a n-sized array, and that is equal to 2 times t of n by 2 plus m of n. Now what is m of n over here? This is the merge complexity. Okay, and it turns out that we can merge the two arrays that we get from the smaller childs in order n. Okay, now if we can merge the solutions in order n, so this would be something like 2 times t of n by 2, right, plus order n, right? So what is the complexity of this recurrence? T of n equal to this, we know using Master Theorem that this is equal to order n to the power log of 2 base 2, that is equal to order n, and since these are same, we just add a log n to it, so this will be taking us order n log n, and that is quite known a fact that merge sort takes order n log n time, right? But how do we merge these two values? That's still not discussed, so let's quickly discuss that. So given two arrays that is sorted initially, how do we merge it into a bigger array which still is sorted? So if we come out of this both being sorted, how do we get this sorted, right? That's the whole problem. So this is like a code portion of it, that how we can sort the whole array by just merging the sorted solutions of a and b. So let's say this is a and b, and we need to merge the solutions into array c. Okay, so we keep I, j and k all 0, so these are the red pointers that are shown over here. Okay, and the idea is whenever you need to take one element, C out of the elements that are being pointed in A and B, which is smaller, and put that in C. Okay, so this is the whole merge routine that is used in merge sort. See the smaller element in A and B, which is being pointed currently. So let's say this is smaller. Okay, let's say this is smaller than this. Okay, so what you do is that put this element over here and increase both the pointers to this part. Okay, now you will again compare this and this. Okay, let's say this comes out to be smaller, so you place this element over here and then update its pointer and the next pointer over here in the C over here. So this is termed as I in the code, this is termed as J in the code, and this is termed as K in the code. Okay, so these are the three values that we're keeping, so three indexes in the array. And if A of I is less than B of J, so we copy the value of A and increase K++ and I++ after this, so these are post increments. Okay, similarly, if B is smaller, then you take B. Okay, now after this while loop runs till one of them ends out of the array, right? Let's say you were at some possible case where everything over here was less than this element, so you keep on adding the elements of I and you reach I over here, something outside the array. Okay, and you have filled in a lot of values over here. Let's say it's a 4 values you have filled from over here, and now you are out of this loop because now I is no longer less than a dot size, that is, it's not in the bounds of A. So now you will still need to add the rest of the elements of J in the B, right? In the from the array B to C, right? So for that you can write just these 2 lines of code without checking which one ended. So if you write this, what this means is that if there are some elements in A, put them in B, in C at the end, and if there are some elements in B, put them in the end of C as well. And we know that this only terminates when one of these ends, right? So only one of these other loops will work. So in total, both of this I, J and K are only walking forward. So this, all of these loops over here will take us only order n, right? So in this way we can merge 2 values in 2 sorted arrays in order n. Now a nice application of this would be, how do you get a sorted array from 3 sorted arrays? So idea remains the same. You have 3 pointers pointing to 3 of them, so all the 3 sorted arrays have 3 pointers pointed to them, and take the one which is smallest and add it to this. Okay, and increase its K pointer. That's it. That's the whole idea. Even if there are n number of lists, you can merge them using this whole idea. So finding that minimum element will become non-trivial when the number of elements in the lists become large. So in that case, you will need to maintain some sort of data structure to get out which array has the smallest number of which has the first smallest element. Like out of all the pointers that are being pointed right now, out of these I, J and so on, like whichever pointers are there in the array, which has the smallest element, and put that element in C and increase its pointer. So this has to be maintained, but this idea of merging sorted lists can be extended even for more than 2 elements, right? Two arrays. So what if there are equal elements in this? The thing is, we don't need to worry which one of the pointer to increase, because anyways this is being sorted. So if let's suppose there was 3 over here and 3 over here, and then next has 5 and this has 6, we don't need to worry about which pointer to increase. We can increase any of them. So if we put 3 over here, let's suppose this 3, and then this I pointer moves to this, then this 3 is still smaller than this, right? So the next element will obviously be this 3, and then this will move. So the order might change, but the value would remain the same. So these 3 will all come first before 5 and 6. So you can increase any of them. That's not a problem. Okay. So this is the whole idea of merge sort, that you divide it recursively. So you can maintain a function. You can, let's say, you can maintain a function which merge sort m with let's call it m sort, okay, and call it on the array A from the range 0 to n minus 1, okay. And in general, any m sort of A L R divides it into two part, okay, and both of these signature will have something like A L to L plus R by 2 and A L plus R by 2 plus 1 comma R, okay, something like this. You divide into two parts and then merge the solutions of this, okay. using this routine. Okay. So this will take us just order and log n to sort the arrays. So what is the difference between any general recursion based ideas like recursion on dynamic programming and this divide and conquer idea? What is the difference? Even in those as well, we call the smaller subproblems and then like use their solutions or whatever they return to get the value of the current solution that we want to solve, current problem that we want to solve. So how do we differ from those? So the main point where we differ is this divide and conquer idea works on non-overlapping subproblems. So let me explain what that means. What is this non-overlapping? Okay, non-overlap. Okay, so what is this non-overlap term? So divide and conquer is a recursive idea itself. So actually this DNC is a subset of recursion. Okay, so we use recursion to implement DNC, so that's not a problem. It's like a subset of recursion. There are many more techniques, but what particularly differentiates DNC ideas from general recursion ideas is that the problem that you have, you cut it into two non-overlapping parts. Okay, so remember in the merge sort, this array got split into two parts. Okay, and none of the elements in these two parts were common, right? None of these two elements in the two arrays were common. So these two problems are completely non-overlapping, like there is no common element in between them. Okay, and so these two subproblems are completely disjoint and are not overlapping. So this is the whole idea, that when you disjointly separate out the solution space, the problem space, into two parts and then recursively solve them, there is no chance of overlap, and these non-overlapping solutions are the things that you get solutions from. And can you find out the solution of the original problem using non-overlapping subproblem? That's the main question. If you can, then DNC is good to go. You can use DNC to solve that problem. But in most cases, like recursion problems, like let's take the most trivial recursion problem like Fibonacci. The Fibonacci of n would be equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So as you can see that this is not like exact division of n into two parts, right? In divide and conquer, we mostly try to divide it into disjoint parts and most importantly non-overlapping. So once you divide it in disjointly, none of their solution space, like none of their smaller problem spaces will actually overlap in any case. Like this cannot overlap, right? In Fibonacci, what happens is that if you write f of n minus 1, that is equal to Fibonacci of n minus 2 plus Fibonacci of n minus 3, right? And as you can see that these two subproblems actually overlap, because this will call something which is used by this, right? So these are like overlapping subproblems. This will call something, this over here, which will overlap with this. So these are not non-overlapping. So in divide and conquer, we mostly have non-overlapping subproblems, and if we can reconstruct the solution of the original problem from the non-overlapping subproblems, then we are good to go and use the DNC problem. Okay, so that's all for divide and conquer idea. See you in the next video.